as I said to you, and he cannot see this source. And then he will, what he hears can be regarded as something coming from this top end. So this distance is very important. Right? And also the amount of sound energy, sound is radiating from this scattered or radiate, doesn't matter for us. It depends on the distance from here to there. So let's denote that distance is A, and this is B. Okay? And I want to compare that distance A and B with respect to wavelength. Okay? But that's not enough, because this essentially means that I am drawing circle. If I put the source over here or receiver over here, this measures are same. In other words, it cannot express the position of source and the position of listener, or in other words, the relative position of listener and source. So we have to invite another length scale. That means how far the source is from the receiver. Geometrical distance, right? So that I denote that is D. And Fresnel lambda simply measures A plus B minus D divided by lambda half, because half lambda is certainly expressed maximum and zero, right? Doesn't really matter, and we call this Fresnel lambda. And we found that the transmission loss using barrier is very much related with this convenience of Fresnel lambda. That means we don't have to look at our famous appendix derivation to get the P, Y, Z when I have incidence angle that has angle of incidence of phi. Okay? We can use this approach, of course, but practically we can use this famous formula. That is 20 log 10 square root of 2 pi Fresnel number over hyperbolic tangent square root of 2 pi NF plus 5 dB and NF greater than 0. That means if I know Fresnel number, then I can obtain transmission loss. Right? This formula is extremely useful For example, suppose we have a car over here in the highway, okay, and maybe one of very brave students who took the acoustic course taught by me, he knows how much transmission loss he will get if he have a sound barrier. So he bravely bought the land over here because the land was in the market in very low price, and he's designing making a good house over here. Okay. And he argued to his good girlfriend, say, I can build a house that has very low noise, and he guaranteed that during the night, I guarantee that the sound inside of a house is 30 dB, and how he can design it, right? To design this, first he has to know personal number, right? He can estimate D, okay? And then also he can estimate A and B by seeing nominal height of sound barrier. And then using this formula he calculates transmission loss. And he found that, the traffic noise in this case normally 90 dB. And using this formula, he found that the transmission loss he can get is only 25 dB. At the frequency range, for example, from 200 Hz to 3 kHz. Suppose that this is the sound coming from the car. Okay? Then how much transmission loss he has to get additionally to keep the promise he made to his girlfriend? 75, 90, so 75, 65. So he has to get 35 dB more using the word. Right? Wrong? 35 dB. Then you can use mass law. Right? So mass law says the Bloch's frequency is, what is it, 123? 1, 2, 3? 1, 3, 2, okay. Doesn't really matter, right? Because we are handling dB, 132, 123, 130, that's okay. Divided by mass per unit area. So suppose I pick up the brick. So how the brick per square meter would be how much the mass would be more than 1 kilo, right?